Welcome back to our AP Chemistry Notes. We're in the Chapter 11 talking about Kas, Kbs, and eventually we'll get to buffers. And that really wraps up our year with how we apply equilibrium to acids-bases situations. Today we're going to look at how we deal with polyprotic acids and bases. And I'll kind of demonstrate it as with polyprotic acids. And it can be applied just as well to, say, a polyhydroxic base, if that is the way we call that. But bases with more than one hydroxide. So polyprotic acid, poly means many, protic for proton, meaning that H+. Because remember, hydrogen is one proton, one electron. H+ then means it's lost the electron, it's just a proton. So H+ and proton are the exact same thing. When we have a polyprotic acid, they can give off more than one H. So each time they can give off an H, we have a different Ka value. Now previously we treated them in a balanced chemical equation as if they gave off all the possible H's, and we just assumed that that was the way it was. Well, each one actually has an individual Ka. We expect it to be more and more difficult, that is, need more and more energy, so it's less and less likely to occur as the ion becomes more and more negatively charged. So for phosphoric acid, the first H is not too difficult. You'll notice that is a relatively high Ka value. I know that seems like a weird thing because that's a negative exponent, but since it's low, that means Ka is rather large. So this H will pop off pretty easily, leaving us with this ion. Now this ion already has a negative charge. To lose another H, well, already we have an opposites attract sort of situation. So it's going to be even more difficult for the second H to come off, but not impossible, and we have measured that, and we have determined the Ka for that is this. Now notice at the large jump in the negative exponent, meaning the Ka is a lot smaller now, much less than 1. So noticeably big difference there between the first and the second, mostly due to the fact that the rest of the ion already has a negative charge. It's going to be hard to lose a positive when opposites attract, Coulomb's law. But it does happen, and let's say that ion, now with a -2, loses a hydrogen. Well, you can imagine if it has a -1 charge and it's difficult with a -2 charge, it's really difficult. So it does happen, but it happens incredibly tiny, and you'll notice again a large jump. So this was like 10,000 times less likely to occur than that, and this is 10,000 times less likely to occur than that. Still can happen, still possible. It just needs so much energy to do that. It's not statistically likely to happen often. Now, of course, in a beaker with 100 milliliters of phosphoric acid, I've got probably, 10 moles of phosphoric acid. So that's 6.02 times 10 to the 24 molecules of phosphoric acid. So yeah, statistically, some of them are going to get enough energy to ionize, to separate like that, to dissociate. But not as many as the charge on the ion grows. So, what if I wanted to know then the total amount of hydrogen ion this acid would produce in all? I would need to be able to add up all three of these hydrogen amounts. Okay, well, we have a Ka, so I can determine how much hydrogen that is. I would draw a Rice table, and I would put in some minus x's and plus x's, and with my Ka, and I may or may not be able to make an assumption, and I would see how much hydrogen ion that is. And then I would do the same for Ka2. I would use Ka2 to see how much hydrogen ion that is. Again, a Rice table, a minus some x's and some plus some x's, and I would solve for x and see what that concentration is. And then Ka3, I would do it again, and I can get how much that is. And then I just add those totals up, okay? So not hard, none of that's really difficult. Is it time-consuming, repetitive, and gives you this feeling of redundancy? Absolutely, but that's what we would need. If I really wanted to know how much hydrogen, say 1 molar of phosphoric acid would give me, I would have to do that calculation 3 times, one for each K, and then add it all up. Now check this out. I did the calculation for us, and for that very last K, Ka3, which was 3.6 times 10 to the negative 13. Well, keep in mind that Kw, water itself dissociates at that amount. So it's only 10 times stronger than water's own dissociation, and we don't expect water to dissociate much at all. So does that mean we might be able to ignore that final Ka? Well, yeah, actually, because if we started with a reasonable amount of phosphoric acid, 0.10 molarity phosphoric acid, which is rather typical and reasonable for an acid, that last Ka only gives us that much hydrogen. Again, with the 6.022 times 10 to 24 molecules available, only that many of them will actually dissociate to give us a hydrogen ion. Now you can see with all those zeros, that's going to make no difference to our results in the end at all. So what that means is really, I don't have to do 3. It means all I need to do is say, hey, I'm going to take care of this. What it means is I can do the first 2, add that up, and that will be, in consequence, that would be all the H that really is going to be around. Because this H that would be made is so incredibly tiny, it's not even worth worrying about, certainly not worth the effort in solving for. So it's a shortcut. That cuts us down from 3 rice tables and 3 solving for x's to just 2 rice tables and 2 solving for x's. Okay, yeah, I know that's still 2, but it's better than 3. So a good rule of thumb, if I could go the correct way here, a good rule of thumb that I propose for you to consider is times 10 to the minus 9. If a Ka, or Kb for that matter, is something times 10 to the minus 9 and larger, it's typically not going to make an appreciable amount of hydrogen ion or hydroxide ion, so you really can ignore it when it comes to adding it in with the other hydrogen amounts or the other hydroxide amounts. Okay. Now this is of course assuming that this is like for a Ka2 or a Ka3. If this is your Ka1, you don't want to assume that that can be ignored, because then your answer is a nothing. So you just work it out like you normally would with 1 rice table and your Ka value and solving for x if it was your first Ka. But with a second Ka or a third Ka, tells you can ignore that, and that saves you a rice table, saves you a solving for x, saves you the time and that feeling of redundancy. Now with that all said, that's about the way we have to handle it, but the way I would consider it being seen most likely on the AP exam is more like this. I can totally see a question, especially for response like this, could also be multiple choice, probably not likely because you would want some help from a calculator, but it could be multiple choice. So there we go. Here's my situation. I've got 0.10 molarity of sulfuric acid and I have a Ka2. Now first thing I want you to realize is, what am I missing? I don't have a Ka1. So why do I not have a Ka1? I hope you said it's because sulfuric acid is a strong acid. And how did you know sulfuric acid is a strong acid? Because you've memorized it as a strong acid. That's the short answer. The better answer is there's no Ka, meaning it never reaches equilibrium. The first ionization of sulfuric acid is a one-way arrow to give us H plus and HSO4 minus. Now I know that in the past you probably thought both H's pop off, and that's entirely how we treated it in the past, but you know better now. So 1 H at a time is the way you need to take it. Well, alright. So if I'm taking a 1 H at a time and that's a strong acid, then it is a one-way arrow. So if I started with 0.1 molarity there, then with a 1-to-1 ratio and a guaranteed has to go to completion, one-way arrow, not an equilibrium, that's why I can't write a K for it, I'm going to get 0.10 molarity of H+. So honestly, that much is done. There's the first ionization amount of H+. My concentration of H+ from my first ionization is 0.1 molarity. Okay. Now we need to see what the second ionization is going to give us. So I'm going to write HSO4 minus, and this is going to be an equilibrium because I have a Ka, and it's going to give me H plus and SO4 2 minus. So my goal is to calculate this so I can add it into that and get a grand total. Okay. How much of this do I start? How much of this do I start with? Well, I don't know, but I should know because over here we said it's a 1-to-1 ratio. Well, it's still a 1-to-1 ratio. So I'll make that much of that. So I'm starting with 0.10 molarity of that. And I'm going to pretend I'm starting with 0 amount. Now you can stick that there, and then the addition just happens in your Rice table. It would make no real difference, but I'll just do that at the end. The point is just decide. It also, if you do it at the end, makes the math a little less tricky. I'll get to that in a minute. Now this is an equilibrium arrow, so how much of this will I lose? I don't know. How much of it will I gain? Well, it's a 1-to-1 ratio, so I gain X amount if I've lost X amount here. So I have 0.10 molarity minus X, and I have X here, and I have X there. Okay, great. So I'm ready to write my Ka expression, which is concentration. Get the points for the formula. Be sure you're putting the charges in with the formula or it doesn't work. Okay, that's what they're looking for, is that you have the exact correct to the charge thing written. I have all 1, so I have no exponents. Okay, and on top I have x squared, and on bottom, 0.10 molarity minus x. Okay, can I assume that x is going to be small? Well, check out our Ka. That's just times 10 to the minus 2. Honestly, we should not assume, and we should use the quadratic equation. Now, I'm not expecting them to ask you to use the quadratic equation on the test, so for the sake of discussion, let's pretend we'll assume. We'll assume that that is approximately equal to 0.10 molarity, and we'll come back and we'll check on that, and let's see if you can figure out whether we can safely assume or not. That's what I want to go with as I'm doing this example problem. Okay, well, not that. Come on. Okay, so that's how my Rice table looks right now. That's how my Ka looks right now. And then, you know, it's ultra fun calculator time, everyone's favorite time of the day. Calculator time, yay. Okay, so I'm going to now multiply my Ka by 0.1. And then I'm going to square root that. And here's what I get. X is equal to, let's leave it in decimal form. It'll make it easier to add in just a moment. 0.03464. I'm just writing some random amount of significant digits for now, so we can talk. Now the label is molarity. There we go. What did X equal? Well, X equaled H plus, X equaled SO4 minus, and X equaled how much I should subtract from there. Okay, so if I start with 0.1 and I subtract that, okay, what amount am I subtracting? I want to point this out. So if I'm taking that and I divide by 0.1, I see that, and times 100 to get percentage, I see that I'm subtracting a really large amount. So it really is not safe to do the assumption there. I should use the quadratic equation. Okay, did you hear that? Because 0.10 minus the 0.03464 is going to give me a huge difference. I'll write it here. 0.06536. Okay, that's like a 35% loss. That is not something we can assume away. So the lesson of this conversation right now is we cannot make the assumption. You would want to put a minus x here, and you'd want to do the quadratic equation. Okay, so what do you do to do the quadratic equation? Oh, you do lots of fun math. You work it out, you FOIL it, and then you Google quadratic equation solver and you type it in, and it's lots of fun. Okay, so I'm going to trust you to do that, and your answer when you use the quadratic equation is going to be a little bit different than this number here. But again, I'm not expecting them to give you something with a quadratic equation on the test. I'm expecting them to give you something that you can estimate. So let's pretend we could, just for the sake of finishing the problem, because that's quite likely what's going to happen on the AP exam. And they know that some calculators you can program in the quadratic equation or download a quadratic equation solver if it's not even built in. Probably somewhere a lot of calculators have it built in. And they know some calculators have, if you're just add, subtract, multiply, divide, and log, you have no ability to do that, and you have to do it all with, pencil and minus b plus or minus square root 8, all that fun stuff. So they're very less likely to ask to do a quadratic equation. So we are pretending that this number is a valid number. We should use a quadratic equation and use the real value. Feel free to pause and work it out and plug it into quadratic equation solver and get your real number to work with. But I just don't care, because I want to demonstrate what to do now. This number not only represented how much to subtract from here, it represents the amount of these two, and the thing that I'm interested in is that this number represents the additional amount of h plus. So if that's representing the additional amount of h plus, well, what word have I been saying a lot? Additional. So this is the amount of h plus I get from the second equation. There's the amount of h plus I got from the first equation. And so I'm going to say that the total concentration of H plus is going to be equal to 0.10 molarity plus that there, 0.03464 molarity. And it looks like I need to round to the hundredths place. So when I round to the hundredths place, I get 0.13 molarity. Here's my final answer there, if it would let me box it. Okay, no, go back, thank you. So that's how we would work that equation. Okay, this is what I would see as very probable if you were asked to do anything about the concentration of H on the AP exam. Because check out what this proves. This proves chemistry that you know a strong acid when you see it, and that you know a strong acid is a one-way arrow, and that you can keep the ratios going, whatever ratios those are. This also shows that you would know how to build a Rice table and use a Ka to solve for an unknown when it's a weak acid, and they'd probably give you an acid much weaker than that so that you can make the assumption. And then that you know to add up the totals. Okay, so I don't know what's on the exam this year, obviously, but if they wanted one question that would prove, the difference between how to work a strong acid and a weak acid, and how a Ka works to solve for X, and how to find a total H plus, then you know what? This has achieved that. And probably then they would even take it a step further, and from here you could find a pH. Because pH is negative log concentration of H, and I have a total concentration of H going on there. Okay, so with that said, I would just, in the calculator, go negative, and once I find the log button, I go negative log and type in my 0.13 molarity, and I see I have a pH of 0.8. 2 sig digs 0.89. And yes, that's very low because this is a very strong acid. So there we go. Okay, so that's how you would want to go about working a diprotic or multiprotic, multihydroxic base 2 would work the same way. check to see if the first ionization is for strong, and use a one-way arrow, and just use the ratios. And then for every weak one, you need a Rice table, and you need a Ka, and you need to solve for x. Now, how do you know it's weak? If you can if you can look up a Ka, and it's less than 1, if it's times 10 to the negative 1 at least, then consider it weak easily. Because a strong acid should be much, much, much larger than 1 when it comes to Ka. So there we go. For every acid that does not start strong, you're going to have a Ka1 and a Ka2 and maybe a Ka3, and you're just going to have to do that many Rice tables, and you're going to have to do that many solves for x's, and then add it all up in the end. So I really hope you're noticing the difference now. For strong acids and bases, we can assume one-way arrow, and it's all by the ratio. Then for every part of that that's a weak acid or weak base, you're going to need a Rice table, and you're going to need to solve for your proton or your hydroxide, and you're going to need to add them all up in the end, something like that. So that's how we work these problems if we have more than one. We see if we have a strong first ionization. If so, that makes that part easier. If not, start a Rice table. That's what you do. If you get a number for a later one, not the first one, but maybe like, okay, if it would go to the screen I want it to go to. Come on, there we go. If we get a Ka that gets beyond, okay, there's apparently a large lag. If we get a Ka that's beyond 10 to the minus 9, you can skip it. Now, if you skip it, you write a note while you're skipping it. I would literally write, I will not add the H from this ionization. Because of the size of Ka, the added H will not be noticeable, or something like that. That's what I would say. A one-sentence statement, not saying that I forgot to, because if you write nothing, it might look like you forgot to add in your third Ka here. But you would write a sentence or some sort of statement saying that you don't need to do it because it's not going to make a noticeable effect in your total concentration of H. All right. So hopefully that helps, and we certainly will be doing some practice over this. You can imagine it takes some time. It is time consuming when you have a lot of K's to use to calculate X's all for one particular problem, but that's what we do sometimes. And again, we're looking for the shortcuts of, can we use a strong acid, strong base in the very first reaction? And it will always be the very first reaction. Or does one of the last reactions, does it have an exponent greater than 10 to the minus 9 so we can write a statement that we're going to ignore it? Those are our shortcuts. Otherwise, for every ionization, you need a Rice table and a Ka, and you need to solve for x. So good luck on your assignment.